Hi, in today's session, we'll discuss all the competitive examination questions and also the tough questions of the entire physics syllabus throughout. Now, dealing with this question, we have calculate the angular acceleration of a flywheel if a flywheel gains a speed of 540 rpm in 6 seconds. Now, basically we have n as 540 rpm, so we convert it into rps or hertz, so we get it 540 upon 60, 9 rps, 9 hertz. Now alpha has been demanded and t has been given as 6 seconds. We use kinematical equation omega is equals to omega naught plus alpha t. Keeping the initial velocity as 0, omega is equals to alpha t, if 2 pi n is equals to alpha t, because omega stands for 2 pi n. We required alpha, so alpha is equals to 2 pi n upon t, that is equals to 2 pi into 9 by 6, which gives me 3 pi radians per second square. The next question. A motorcycle is going on an average overbridge of radius r. The driver maintains a constant speed as the motorcycle is ascending on the overbridge, the normal force on it. Now we have r is equals to mg cos theta minus mb square upon r. My weight will always be acting vertically downward, and this is my normal reaction on the vehicle. So therefore, if this is vertically downward, this can be resolved like this. So my normal component is actually balanced by mg cos theta minus the centripetal force. So mg cos theta minus mb square upon r. So if theta is if it's ascending, that means theta is decreasing. So if theta is decreasing, I would say cos theta would increase. Hence, r is directly proportional to cos theta. Therefore, r also increases. Option A. The next question. A mass m on a frictionless table is attached to a hanging mass m by a cord through a hole in the table as shown in the figure. So as we can see, this mass is attached to a hole through a string. Okay, so the angular speed with which m must be spin for m to stay at rest. So the angular speed with which it should spin so that it stays at rest. Now, we can say the condition for m to be at rest when m is spinning is mg is equals to mv square by r. That means the weight mg of this block should be balanced by the centripetal force. Now we can say mg is equals to mr omega square, another formula for my centripetal force. Now they have required the angular speed, thus we have used this formula. So we can say omega square is equals to mg upon mr. So now if I want omega, this becomes under root of mg upon mr. So mg upon mr under root, option A. Next question. The distance between the rails is 1.5 meter. I would say this as A is equals to 1.5 meters. And the center of gravity of train is 2 meter from the ground. So H is 2 meter from the ground. So the maximum speed of train on a circular path of radius 120 meters can be. So G is given as 9.8, we'll say 10 meter per second square, and V is being demanded. Now for maximum speed, mgr or mga should be equals to mv square h by r without overturning. So therefore GA is equals to m and m will cancel, you get v square h upon r. So therefore v square is equals to GAR upon h. Therefore v is equals to under root of GAR upon h, that is equals to 10 into 120 upon 2. So that is root of 441, that is 21 meter per second. Option C. The next question is, a pilot of mass 81 kg, so we have mass as 81 kg, loops a loop, so that is performing vertical circular motion with steady speed of 300 kilometers per hour. We have speed as 300 into 5 by 18 meter per second. That is executing vertical circle. If radius is 0.5 kilometers, r is 0.5 into 10 raised to 3 meters, which is 5 into 10 raised to 4 meters. Then the force with which the pilot is pressed into the seat at the highest point. So we required force at the highest point. G is to be taken as 10 meter per second square. We can use the condition for tension at the highest point, which is mv square upon r minus mg. So this becomes 8 into 300 into 5 by 18 the whole square upon r, that is 5 into 10 raised to 4 minus mg, that is 81 into 10. So on solving this further, I get it as 1125 minus 810, which is 315, that is 3.15 into 10 raised to 2 Newton. Option A. Now the next question, let F be the force acting on a particle having position vector r bar and tau bar. Be the torque of this force about the origin. So the following conditions are given and we have to classify whether these conditions are true or not. Now let us see the first condition. It is r bar dot tau bar equals to 0 and F bar dot tau bar also equals to 0. Now, if we focus, r bar and tau bar are mutually perpendicular from this formula. That is, the definition of tau bar is r bar cross F bar. So if two mutually perpendicular vectors and a cross product have been taken, then the third vector is also a mutually perpendicular vector. That means tau bar is perpendicular to r bar as well as F bar. So if I take r bar dot tau bar equals to 0, that means RT cos theta or r tau cos theta equals to 0, and if theta is 90, this is correct. This r into tau is 0. Similarly, that goes for F bar dot tau bar. So this condition is correct. Let us check one more condition and verify whether our answer is correct or not. I have r bar dot tau bar not equals to 0. Just now we have proved that it is equals to 0, hence this is wrong. Even F bar dot tau bar not equals to 0 is wrong. It is equals to 0. That means any of these conditions from B, C and D are not correct. Only option A is correct. Now we have the next question. A rod of weight W is supported by two parallel knife edges A and B. So we'll draw a rod A and B and is in equilibrium in a horizontal position. The knives are at a distance D from each other. Alright, so knives are at a distance D from each other. The center of mass of the rod is at a distance X from A. Now exactly we don't know where the center of mass is, so we can say this point is X. So this distance becomes X. Therefore, by default, this distance becomes D minus X. Its weight will be at the center of mass W. Alright. So, the normal reaction on A has to be calculated. So, NA has been demanded. Now, this is a question related to equilibrium, that is conditions of equilibrium. I would use condition of rotational equilibrium over here. Now as we can say, the normal reaction or the combination of normal reaction of A and B both balances my weight. So if I want NB from here, it will be W minus NA. So this becomes my equation number 1. Now, torque will always be balanced at the center of mass, or I would say if I take moment about O, I'll have to say that is force into perpendicular distance on the LHS plus force into perpendicular distance on the RHS is equals to 0. Now, this is my LHS and this is my RHS. Now the force on the LHS will be my normal reaction into X, and force on the RHS nothing but NB into D minus 6. Alright. Yep, I will say plus equals to 0. Alright. So therefore on solving I'll get NA into X is equals to NB will be replaced by W minus NA into D minus X plus equals to 0. Therefore NA into X is equals to minus of W minus NA into D minus X. So on simplification, lastly I'll get NA into D is equals to W into D minus X. So therefore NA will be equals to W into D minus X upon D. So normal reaction at A is W into D minus X upon D. W into D minus X upon D. Option is D. Now the next question is, two particles A and B are moving as shown in the figure. Their total angular momentum about point O. So if they are moving at point O, I'll say the vector sum, that means this will go like that. So we have to subtract the angular momentum to get the effective angular momentum at this point O. Therefore, I'll say at O, M1 V1 R1, which is the angular momentum, minus M2 V2 R2 is equals to LO. So therefore, M1 V1, that is 2.8 into 3.1 into 3.6. I'm assuming this as my first condition and this is my second one. Minus M2. M2 is 6.5 into 2.2 into 1.5. So this gives me 9.8 kg meter square per second. Option A. Now the next question is, a thin circular ring of mass m and radius r is rotating about its axis with a constant angular velocity omega. Two objects of mass m are attached gently to the opposite ends of the diameter of the ring. So this is my ring initially of mass m. Now two objects have been placed diametrically opposite of masses m. The wheel will now rotate with angular velocity. Alright. Now, in the first condition, when these masses were not attached, the moment of inertia was mr square. And then in the second condition, I would say it is m plus 2m into r square. Now, by law of conservation of angular momentum, I get L1 is equals to L2, that is I1 omega 1 is equals to I2 omega 2. So this can be said as mr square omega 1 is equals to m plus 2m r square omega 2. I require omega 2. R square and r square will get cancelled. So omega 2 is equals to m upon m plus 2m into omega 1, which is omega. So m upon m plus 2m into omega is option C. Alright. So the next question. When W joule of work is done on a flywheel, its frequency of rotation increases from nu1 to nu2. The moment of inertia of the flywheel about its axis of rotation is given by. So W joule of work is done and the relation between moment of inertia has been demanded and frequency has been given. It's a flywheel, that means it will be a disk. But here we don't need the moment of inertia equation, we need kinetic energy. Therefore I will say kinetic energy is given by half I omega square. But as we all know, its frequency is changing, that means angular velocity is also changing. So if it is half I omega 2 square minus omega 1 square, that is equals to W. So I require moment of inertia, right? I is equals to 2W upon omega 2 square minus omega 1 square. Now if I put omega as 2 pi nu, I'll get 4 pi square common into bracket nu 2 square minus nu 1 square. So 2w upon 4 pi square nu 2 square minus nu 1 square. So students make a silly mistake and they mark option C. But if we see there is a 2 in the numerator, so 2 ones are 2 twos are. So this becomes w upon 2 pi square nu 2 square minus nu 1 square. So the option is A. Now the next question. The moon's radius is 1 by 4 that of the earth. That means r of moon is 1 by 4 that of r of earth, and mass is 1 by 80 times that of earth. That means mass of moon is 1 upon 80 times mass of earth. If g represents the acceleration due to gravity on the surface of earth, then that on the surface of moon is. Now what we basically do, we have a concept in our mind that the acceleration due to gravity on the moon is 1/6 of that of earth. So irrespective of the data, we can straight away mark g by 6. So let us solve and see if g by 6 is the correct answer over here, or we cannot assume it to be g by 6 if some data is being given. Let's solve. Now, GE can be written as GME upon RE square. So therefore GM is equals to GMM upon RM square. But what is GMM? GM, that means a mass of moon is 1 upon 80 times mass of earth, and the radius is 1 by 4 times, that means 1 by 4 RE the whole square. So this becomes GME upon R square is equals to into 16 upon 80. So 16 1 times and 16 5 times. So GME upon RE square is G. So GE upon 5 is the answer. And what would we have marked? That is G by 6, which was the wrong answer. Now, let GH and GD be the acceleration due to gravity at a height h above the Earth's surface and at a depth below the Earth's surface, respectively. If GH is equals to GD, then the relation between H and D is. Now, we all know GH is equals to G into 1 minus 2H upon R. On the other hand, GD is equals to G into 1 minus D upon R. So if GH is equals to GD, we can compare that 2H is equals to D. Option D. The next question is, calculate the angular velocity of Earth so that the acceleration due to gravity at 60 degree, I would say lambda is equals to 60 degree, latitude becomes 0. That means G dash has to be taken as 0. Radius of Earth is 6400 kilometers. Gravitational acceleration at poles, that means GP is 10 meter per second square, and cos 60 is equals to 0.5. Now they have given a hint by using lambda that we need to use this formula. G dash is equals to G minus r omega square cos square lambda. This G is actually GP because the maximum value of G is at the poles. Now this is 0. So this becomes GP minus R omega square cos square lambda. So therefore GP is equals to R omega square cos square lambda. Therefore omega square is equals to GP upon R cos square lambda. So 10 upon 6400 into 10 raised to 3 into 0.5 the whole square. So this will give me 10 raised to minus 2 by 4. Now that is equals to 2.5 into 10 raised to minus 3 radians per second square. That is option D. At point the gravitational potential and also the gravitational field due to Earth is 0. The point is, now let us first write the formula for gravitational potential. We get V is equals to minus Gm upon R, and we also write gravitational field, say I is equals to Gm by R square. Now from here we can see that V is inversely proportional to R, also I is inversely proportional to R square. So if V has to be 0, that means R has to be at infinity, and the same is applied for the field. So V is equals to 0 and I is equals to 0 if R is equals to infinity. Option D. Now, how does the escape velocity of a particle depend on its mass? Now, this is a good question. I would say escape velocity of a particle depend on its mass. Now, we'll write the formula of escape velocity as under root of 2gm upon r. If we see, it only depends on mass of the planet and not the body. So from the following option, m is absent. So m can be equals to 1 if I write m raised to 0 in the above formula. Option C. Another question. The escape velocity from the surface of Earth is VE. The escape velocity from a planet whose mass and radius are 3 times those that of Earth. Again we'll write V is equals to under root of Gm upon R. Now VE is directly proportional to root of m by R. So for VE1 is equals to upon VE2 is equals to under root of m1 upon R1 into R2 upon m2. Now we all know m2 is equals to 3m1 while R2 is equals to 3R1. So therefore m1 upon R1 into 3R1 upon 3m1, everything will get cancelled. Therefore VE1 is equals to VE2. That means the escape velocity will remain same, VE. Option A. Now, two similar wires of steel and copper are stretched with same force. The Young's modulus of steel and copper are. So we have Young's modulus of steel as 20 into 10 raised to 11 dyne per centimeter square, and Young's modulus of copper, that is 12 into 10 raised to 11 dyne per centimeter square. The ratio of the increments in their length, that means E1 upon E2, has been demanded. Now we know the formula of a Young's modulus. Young's modulus is equals to stress upon strain, that is longitudinal stress upon longitudinal strain, which is mgl upon pi r square E. Therefore from here we get y is inversely proportional to E. Therefore y1 upon y2 is equals to E2 upon E1. Therefore we get 20 into 10 raised to 11 upon 12 into 10 raised to 11, that is equals to E2 upon E1. But the requirement is E1 upon E2, as they want from steel to copper. So therefore this becomes 12 into 10 raised to 11 upon 20 into 10 raised to 11. This will get cancelled and we'll get this as 3 by 5, that is 4 3s are and 4 5s are. Option Bombay. Now this is a good question. The given graph shows that the extension delta L of a wire of length 1 meter. So we have the length of wire as 1 meter from the top of a roof at one end with a load W connected to the other end. If the cross-sectional area of the wire is 10 raised to minus 6 meters square, calculate the Young's modulus of the material. Y has been demanded. Again, the given graph shows the extension delta L of a wire of length 1 meter suspended from the top of a roof. So a wire suspended from the top of a roof by some weight, maybe by some force or load, connected to the other end. If the cross-sectional area of the wire has been given, calculate the Young's modulus. Now to calculate the Young's modulus, I require Y is equals to FL upon AE. Now, as I can see, it's a straight line passing or maybe uniform after 20 Newton, and there's an extension of 1 into 10 raised to minus 4 meters. I would assume it to be and take this condition as my favorable condition, that is 80 and 4 into 10 raised to minus 4 as my extension. So my force will become 80 into length is 1, area is 10 raised to minus 6, and this becomes 4 into 10 raised to minus 4. So if I cancel this becomes 1 times 20 times, and this goes at 20 into 10 raised to minus 10, that is equals to 2 into 10 raised to, this becomes plus 10, and this will become 2 into 10 raised to 11 Newton per meter square. So a question which looked a bit confusing but very simple. So in such questions we can assume any one condition and we can solve it very simply. So the required answer is 2 into 10 raised to 11 Newton per meter square, option A. Alright. So the next question now. The normal density of gold is rho and its bulk modulus is K. The increase in density of a lump of gold when a pressure P is applied uniformly on all sides. The increase in density has been demanded, that means delta rho is equals to question mark. Bulk modulus has been given and pressure P has been given. We know a relation that K is equals to P delta V upon V, that is VdP by dV, or vice versa, that is V upon delta V. Therefore delta V upon V will be P upon K, and we have a relation between density and volume, that is density is equals to mass upon volume. So therefore delta V upon V is equals to delta rho by rho, that is equals to P upon K. So therefore delta rho is equals to rho P upon K. So rho P upon K, option A. Now the possible value of Poisson's ratio is, now we need to remember this very carefully, that Poisson's ratio range is -1 to 0.5. Always do remember it. That's why this question has been selected, so that we do not waste our marks on such easy questions. So -1 to 0.5, so only the option 0.4 matches it, so option D. Again a similar question, minimum and maximum values of Poisson's ratio for a metal lies between, so minus infinity to infinity, no, it says from -1 to 0.5, so 0 to 0.5 comes in this range, hence we'll select option D, which is correct. Now the next question, a wire can be broken by applying a minimum load of 20 kg weight. The minimum force required to break the wire of twice the diameter. That means if R or diameter is equals to D1, then the force required to break F1 is 20 kg weight. So if diameter is 2D, that is D2, then F2 is equals to question mark. Now if diameter is becoming double, that means radius is becoming double, so I can say R2 is equals to 2R1. Therefore we need to find the relation between force and radius. Now we can say the breaking stress should be same. That means F1 upon A1 is equals to F2 upon A2. So therefore F1 upon pi R1 square is equals to F2 upon pi R2 square. So therefore F1 is 20, pi and pi will get cancelled. 20 upon R1 square is equals to F2 upon R2 square. So therefore F2 upon 20 is equals to R2 by R1 the whole square. So what is R2? 2R1. So I get F2 upon 20 is equals to 4R1 square upon R1 square. Therefore F2 is equals to 80 kg weight. Option C. The next question, a metal rod of length L, cross-sectional area A, Young's modulus Y, and coefficient of linear expansion is heated to alpha is heated to T degrees Celsius. The work that can be performed by the rod when heated is. Now if I want work, so W is equals to force into displacement. First of all, we'll calculate what is thermal strain. Now we know thermal strain is equals to alpha delta T. Here it's alpha T. Therefore, thermal stress will be Young's modulus into strain, that is Y alpha T. Therefore, force is stress into area, that means Ya alpha T is my thermal stress. Okay, now work done in elasticity is the formula is half into F into your elongation. Therefore, I can say this is half into Ya alpha T. Now I need to find out the elongation, so I'll say L T minus L naught upon L is alpha T. Now this is strain. So if I want delta L, which is LT minus L naught, it will be L alpha T. So if I put half into Y I alpha T into L alpha T, this will become Y upon or Y A alpha square T square into L upon 2. So Ya alpha square T square L upon 2, option B. The next question. The Young's modulus of a metal is 1.2 into 10 raised to 11 Newton per meter square. Y is 1.2 into 10 raised to 11 Newton per meter square. And the interatomic force constant. So interatomic force constant, I would say K is equals to 3.6 into 10 raised to minus 9 Newton per angstrom unit. Now, if you have no clue about interatomic force constant, I would say when we do the chapter KTG and radiations, we know or we come across a topic called as degree of freedom, where we deal in vibrational degree of freedom. So, the particles, they perform vibration, and if the covalent bond is a bit weak, then this particle, that is for carbon monoxide, I would say, we have a spring-like bond, that means a weak bond which vibrates and also rotates. So this vibration can be compared to the motion of spring, hence constant, that is interatomic force constant. Okay, so mean distance has been demanded. So this is a very typical type of question, and it has been less observed in much examinations, but a very important question. So the probability of this questions becomes a bit high in CET examinations. Now, as we do know about this concept, but yes, we can understand this by a single formula, that mean distance is given by force constant upon Young's modulus. Now, if you don't know, how can we calculate mean distance? If distance is demanded, that means meter is demanded. So K is your Newton per meter, while Y is Newton per meter square. So if I divide this, I get Newton and Newton get cancelled, and meter square upon meter. So this meter and square will get cancelled and I get meter. So this formula is correct, and also we decide that A naught is equals to K upon Y. Now what is K? 3.6 into 10 raised to minus 9 upon 1.2 to 10 raised to 11. So this will be 36 by 12 into 10 raised to minus 20. This is 6 2s are 6 6 are 2 1s are 2 3s are 3 into 10 raised to minus 20. Okay, and we have 3 to 10 to minus 9 Newton per angstrom unit. So we did not substitute angstrom unit. So if angstrom is denominator, I'll put it in numerator as 10 raised to plus 10. So now this will become 10 raised to minus 10, and I get 3 angstrom unit as the answer. Now the next is, now this is a topic from standard 11th which has been included in this session because it's a very important topic. The name is mechanical property of fluids, that is viscosity, and it is a very important topic because it deals with fluid mechanics. Now the internal friction in the liquid layers is called as viscosity. But how? Now suppose if I have a liquid drop, very stable, it is made up of different layers of liquids. Now when this drop is placed on an inclined surface, it will move in the downward direction. So this layer will come in contact with the surface and the velocity of the first layer will become 0, while the layer above will try to move in the forward direction and above will further move. So therefore when these layers they move in further direction, leaving this layer at velocity equals to 0, but the molecules here will try to attract these molecules and try to drag them back with some force due to the cohesive force between these molecules. Now this drag behind is called as viscosity, and the force by which these people or these molecules are dragging this layers behind, that means opposing the motion, that to internally not externally, is called as viscous force. Hence it's not the external resistance offered by the surface, it's itself developed by the liquid. Therefore it is the internal resistance of the liquid towards its flow called as viscosity. Now viscosity is the property of the liquids and gases which are closely related to A. Elasticity, inertia, tension, friction. Now this is a very straightforward question. I would say this is friction because what friction does for solids, viscosity does same for liquids. And viscosity in liquids, if we increase the temperature, the viscosity in liquids decreases, while if we increase the temperature in gases, viscosity will increase. Now, a ball of radius r and density p falls freely under the gravity through a distance h before entering the water. So we can see from this distance the ball has been dropped. Velocity of ball does not change even entering water. If viscosity of water is eta, the value of eta is given by, or the value of h is given by. So height has been demanded. We can say if the body is freely falling, v is equals to under root of 2gh. Therefore v square is equals to 2gh. Whenever you see a spherical body being dropped in a liquid medium, you'll straight away think on Stokes' law. Now Stokes' law is basically divided into two parts, that is viscous force and terminal velocity. So here we need velocity, hence we'll deal in terminal velocity. The formula is 2 by 9 r square upon eta rho minus sigma into g. Now r is the radius of sphere, eta is the viscosity of the medium, rho is the density of the body, while sigma is the density of the medium, g is acceleration due to gravity. Now what is v? We have v as under root of 2gh, that is equals to 2 upon 9 r square by eta into rho minus sigma into g. On squaring both sides, I'll get 2gh is equals to 4 by 81 r is to 4 upon eta square rho minus sigma the whole square into g square. We require h. The 2 ones are 2 2s are, g and square will get cancelled, so I'll get h as 2 upon 81 r is to 4 eta square rho minus sigma the whole square into g. So 2 upon 81, okay, and r is to 4 is in option C, g and rho minus sigma. Now sigma has been replaced by 1 because it is 1 g per cc, that is 1000 kg per meter cube, hence option C is correct. Now the maximum average velocity of water required for streamline flow of liquid passing through a tube of radius 1.25 centimeter. So radius is 1.25 centimeter. Coefficient of viscosity is eta 10 raised to minus 3 decapoise. Now maximum average velocity, that means they demand critical velocity for the flow to be streamline. Streamline flow and velocity, we can remember Reynolds theorem. So Reynolds number is the concept. So for streamline flow, Reynolds number should be 2000 or less than 2000. So therefore the formula for Reynolds number is rho v c d by eta, where d is diameter of tube. Now rho, that means it's water, so that will be 1000 or 10 raised to 3 into vc into, now this is 1.25 into 2, that is 2.5 upon eta is 10 raised to minus 3. Decapoise means Newton per meter square second. So therefore, and Reynolds number is 2000. So if I need critical velocity, this becomes 2000 into 10 raised to minus 3 upon 10 raised to 3 into 2.5. So this comes as 0.15 or 0.101 meter per second, which is close to 0.08. That is option C. So it comes at 0.1, that is close to 0.08. See, that's all for this session. Thank you. Hi friends, today we are going to do synopsis of the remaining chapters in the physics of this session. So we'll start with the chapter gravitation, a different chapter and an important one. So we'll go with acceleration due to gravity, that is g is equals to gm by r square on the surface of earth if we need to calculate at a height, this is gm by r plus h the whole square. The relation between gh and g is gh is equals to, or gh upon g is equals to r upon r plus h the whole square. If h is very small than r, then gh is equals to g into 1 minus 2h upon r. An important synopsis that gh is always less than g, or maybe acceleration due to gravity on the surface. The next important thing is variation of g due to depth. We'll talk about GD over here. The GD is given as gm upon r minus d the whole square. GD and GS or G are related as 1 minus d by r. Also, the things to be remembered is GS is greater than GD is greater than GH. So this is the relation between all the three acceleration due to gravities. There is a small graph which shows variation of G. Now this is variation of G. If this is the surface, then going towards the depth it's linear, while going towards the height it's exponential. This is x versus G. Alright, the next concept is critical velocity. It is given as root of gm upon r. It's also given as under root of gr. Along with critical velocity, we have escape velocity, which is given as v is equals to under root of 2gm upon r. Also v is equals to under root of 2gr. If we talk about at height h, the formula for Vc is equals to under root of g into r plus h. Over here this will become as Vc is equals to under root of gm upon r plus h. The relation between Vc and Ve is Ve is equals to root 2 times into Vc. Time period of revolution is given as t is equals to 2 pi under root of r cube by gm. Also we have a relation t square is directly proportional to r cube, very important. Now another concept is binding energy at surface is given as gmm upon r, while binding energy at a height h is given as half gmm upon r plus h. Some of the synopsis or theory part which we need to remember is binding energy is equals to negative of total energy. Binding energy is equals to kinetic energy at h. Binding energy is equals to negative of half of potential energy at h. Okay, now G does not depend on mass of the body. Also Vc and Ve does not depend on mass of the body. value of G is maximum at the poles and minimum at the surface. Now, distance of moon from Earth is 3.85 into 10 raised to 8 kilometers. Acceleration on moon due to Earth is 0.0027 meter per second square. Then we have mass of Earth, which is 5.98 into 10 raised to 24 kg, which is almost 6 into 10 raised to 24 kg. Alright. Now we can say that gravitational potential will become zero if r tends to infinity. So this is all with chapter gravitation. We'll see the next chapter now. The next chapter is elasticity. The most important formulas we'll see is stress is equals to force upon area, strain is equals to delta L upon L or delta V upon V. Also shear strain, that is theta. Now there is a relation between stress and strain, which is called as modulus of elasticity. Young's modulus is given as longitudinal stress to longitudinal strain, which can be written as F upon A into upon longitudinal strain. So you can say that L upon E, because it will be E upon L, so L goes up. This becomes mgl upon pi r square E, where E is the elongation. Alright. We have bulk modulus is minus VdP by dV, where negative sign indicates contraction, that is a decrease in volume and increase in pressure. Then we have modulus of rigidity, which is tangential force upon area into theta. Now we can say 1 upon bulk modulus is called as compressibility. We can say longitudinal strain alpha is equals to change in length upon original length, while lateral strain, I would say beta, is change in radius upon original radius. Alright. We also have Poisson's ratio, which is minus TR upon R, into L by L, which can be written as L delta D upon D delta L. Work done per unit volume, work done is half into F into E, while work done per unit volume, which is strain energy per unit volume, is half into stress into strain. If I need to calculate work done from here, I could say half into stress into strain into volume. Force for the distance x is YAX upon L. Work done per unit volume is also given as half strain square into I. Work done per unit volume is half stress square upon Y. Elongation is more dependent on radius than length. You can say E is inversely proportional to R square and E is directly proportional to L. This is more important than E proportional to L. If there is a comparison between these two in a question, I would neglect this part and only compare the change in radius with the elongation. Now, some more important notes. A quartz fiber and phosphor bronze is nearest approach to the perfectly elastic body. Now water is more elastic than air, as volume change in water is less. For same pressure. Hooke's law is obeyed only for small values of strain. The area stored under the stress strain curve gives energy stored per unit volume. Breaking stress for a wire of unit cross section is called as tensile stress. Last is the measure of deformation is strain. So that's all with elasticity. We'll go to the next chapter now. The next section we're doing is fluid mechanics and surface tension. Fluid mechanics has a lot of importance in theory examination because it has a connection with surface tension there, and the questions can come miscellaneous between fluid mechanics and surface tension. Alright, so first of all we'll deal with fluid mechanic formulas and then surface tension. Pressure intensity is given as H rho G, where H is the depth of the liquid stored, like this. So this is H, and then pressure is directly proportional to H. So as we go into the depth, pressure increases. Okay. The next is here pressure in a air column, that is total pressure in an air column. I would say this air column is half filled with water and half with air. So in this part it is P naught, that means only atmospheric pressure, while here it will be gauge pressure, that is what is pressure intensity, H rho G. So the total pressure is given by P naught plus P gauge, which is P naught plus H rho G. Now there is a small concept in the chapter called as hydrostatic paradox, in which we learn that the shape of the container is not the parameter to measure the weight or force acting on the bottom. So we can say that if the level of liquid is same in all the containers, pressure will be same, hence force acting at the bottom will all be same. Force is bottom, does not change. So pressure does not change with the shape, size or weight of the liquid. It only changes if the height of the liquid column changes. You have Pascal's law. Pascal's law states that F1 upon A1 is equals to F2 upon A2. Now, we also say that force is equals to pressure into area. So force can be given as H rho G into A. Now, applications of Pascal's law. You can say applications of Pascal's law are some mechanical machines called as hydraulic lift, hydraulic press, hydraulic crane, also hydraulic brakes, buoyant force, the force exerted by a liquid on a submerged body. Now, if G equals to 0, pressure at all points is same, and G is not equal to 0, pressure increases with depth. streamline flow. The flow which is continuous, it does not, in which the layers of liquid does not intersect with each other, which is a slow flow, also known as laminar flow. We say discharge is equals to constant, that is Q is equals to constant, and Q is given as area into velocity is equals to constant. Therefore A1 V1 is equals to A2 V2. Now we know viscosity, internal resistance offered by a liquid towards its flow. So if I consider a liquid drop, so the lowest layer is in contact with the surface, and if the drop moves in the further direction, your lowest level will be at velocity 0, but the upper layer will move in the forward direction, and this will also move with further, and also this one. As we go above at the above layer, that means as the distance from bottom increases, your velocity also increases. That means the velocity changes with respect to distance. This is called as velocity gradient. Newton's law. F is equals to eta A dV by dx. If we need to calculate stress from here, I would say stress or tau is equals to eta dV by dx, because F upon A gives me stress. Stokes law. F is equals to 6 pi eta RV, terminal velocity. V is equals to 2 upon 9 r square by eta rho minus sigma into G. Bernoulli's principle. P by rho plus V square by 2 plus GH is equals to constant. Torricelli's law. V equals to under root of 2GH. Reynolds number rho Vc d upon eta. Vc is critical velocity. Of flow. D is diameter of the tube, rho is the density, and eta is the coefficient of viscosity. I have Poisson's formula, that is V equals to pi p r raised to 4 upon 8 eta n. Let's solve with fluid mechanics. We'll start at surface tension. In the chapter surface tension, the first formula that we come is force per unit length. Tension is equal to force per unit length. Now that is surface energy is equals to tension into area, that is tension is equals to dW by dm. Excess pressure is given as Pi minus P naught is equals to 2T upon R for a drop, and Pi minus P naught is equals to 4T upon R for a bubble, especially soap bubble. Angle of contact is dependent on nature of liquid, also nature of the surface in contact. If force of cohesion is less than force of adhesion, angle of contact is acute. Force of cohesion is greater than force of adhesion, angle of contact is obtuse. And if force of adhesion is only present and force of cohesion is absent, then theta is equals to 0. This is the case for pure water. Theta for mercury is 135 degrees to 140 degrees. Rise in capillarity, H is equals to 2T cos theta upon R rho G. There is another formula, H is equals to L cos theta. Also H1 R1 is equals to H2 R2. Work done is equals to 4 pi T R2 square minus R1 square. If you want to increase the radius from R1 to R2 of a droplet, work done is equals to 8 pi T R2 square minus R1 square. If you want to increase the radius from R1 to R2 for a soap bubble, and this is for a drop. So that's the end of surface tension. Next chapter is radiation. Substances opaque to heat radiations are called as atherminous substances, which are transparent to heat radiations, are called as diathermous. Here we can see the examples are water, then wood, copper, iron, lamp black, etc. Here I can see the examples such as glass, quartz, here are gases such as oxygen, hydrogen, and then here sodium chloride, dry air, etc. I'm dealing black body now. It 100% absorber and 100% emitter. For perfectly black body, A is equals to 1, R equals to T equals to 0. It cannot be realized in practice. A hot black body emits more energy per unit area than the cool one. And that is Newton's law of cooling also, that a body which is at higher temperature will radiate more. Alright, so this was all about a perfectly black body. Now we'll talk about emissive power and emissivity. The emissive power is equals to Q by 80. For a perfectly black body it is 100%. For the bodies we can say emissive power is equals to emissivity into emissive power of perfectly black body. We can also say absorptive power is absorptivity is absorptive power to the ratio of absorptive power of a black body. Now we have Kirchhoff's law stating that coefficient of absorption is equals to coefficient of emission, while Stephen's law is stating the emissive power is equals to E sigma T raised to 4 minus T naught raised to 4 for any body. If it's a perfectly black body, put E equals to 1 for perfectly black body. This is not law of cooling. Stephen's law can be extended to represent the net loss of it. Now, Stephen's law is an advanced form of Newton's law. While Newton's law is given as d theta by dt is equals to k theta minus theta naught, also dq by dt is equals to k theta minus theta naught, where k is equals to ms upon dt. Temperature of sun is 6000 Kelvin, where lambda should be 4757 angstrom unit. Now also this is learned from Wayne's law. It also can state that temperature of a violet star is maximum and temperature of red star is minimum. That means higher the wavelength, the less would be the temperature. So you can also say if greenhouse gases does not exist, temperature of earth would have been minus 18 degrees Celsius. The gases released from electronic appliances add to the greenhouse gases and has caused a rise in temperature. So now the chapter is electrostatics. We'll start with the formulas. U is equals to 1 upon 4 pi epsilon naught k q1 q2 upon r12. U is also equals to minus p bar dot e bar. C is equals to q by v. C is equals to epsilon naught a by d. This is parallel plate capacitor where dielectric is absent. When dielectric is present, so with dielectric I would say this is E. C is equals to epsilon naught a d minus t 1 minus 1 upon k. 1 upon Cs is equals to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Capacitor in series. Please focus. Capacitors in series. And for parallel capacitors, Cp is equals to C1 plus C2 plus C3. U is equals to half Cv square, that is equals to half Qv is equals to half Q square upon C. Energy loss, that is equals to U minus U dash is C1 C2 V1 minus V2 the whole square upon 2 into C1 plus C2. Yeah. Shortcuts and synopsis. Direction of the torque is given by right hand screw rule. Now, when two identical conductors having charges Q1 and Q2 are kept in contact and separated. Later, has a charge of Q1 plus Q2 upon 2, and if charges are Q1 and minus Q2, then it's Q1 minus Q2 upon 2. Energy spent by the battery in charging the capacitor is equals to Q into V. Energy per unit volume, that is U is equals to small u is equals to capital U upon volume, that is equals to half epsilon naught E square. Energy stored in parallel plate capacitors. This is U is equals to half epsilon naught E square into AD. So this is the end of electrostatics. These are all the formulas. Now the next chapter. Hi, today we're going to solve some other MCQs in this session. So the first MCQ as we go: the space inside a toroid is filled with tungsten whose susceptibility is 6.8 into 10 raised to minus 5. I would highlight this. So we get susceptibility is equals to 6.8 into 10 raised to minus 5. The percentage increase in the magnetic field will be, okay, so I would name it as percentage increase in magnetic field. Now, as we all know that B is equals to mu naught H into 1 plus susceptibility. So therefore B is equals to P naught into 1 plus susceptibility. Therefore B is equals to B naught plus B naught into susceptibility. Therefore B minus B naught is equals to B naught into susceptibility. Therefore susceptibility is equals to B minus B naught upon P naught. Now if we multiply both sides by 100, so susceptibility into 100 is equals to B minus B naught upon B naught into 100. So this is change in the field, and I would say into 100 gives me percentage change. This is delta B, which is susceptibility, that is 6.8 into 10 raised to minus 5 into 100. So therefore percentage change in delta B is equals to 6.8 into 10 raised to minus 3, which is 0.0068%, and the option is A. Okay, now the shortcut in this problem is, whenever you get such a question where only susceptibility is given and percentage increase or decrease in the magnetic field has been demanded, you can directly multiply susceptibility by 100. The next question: a current of 10 ampere is flowing through a circular coil of 5 turns. So I would say current is been given as 10 amperes and number of turns is 5. We have it for a circular coil. The coil lies in the xy plane. So the coil lies in the xy plane. What is the magnitude and direction of magnetic dipole moment? Now we require magnetic dipole moment. Actually we require m bar because we need the magnitude as well as direction. Alright, so basically m is equals to nia. Okay, there's another data over here where the radius is 7 centimeters. I would say r is 7 to 10 raised to minus 2 meters. So therefore m is equals to 5 into 10 into pi into 7 into 10 raised to minus 2 the whole square. So 5 into 10 is 50 into 3.142 into 49 into 10 raised to minus 4. So this is 50 into almost 50. This gives me 2500. 3.142 as 3 into 10 raised to minus 4. 3 into 25 is 75 into 10 raised to 2 into 10 raised to minus 4. So this becomes 10 raised to minus 2. So 75 into 10 raised to minus 2 is 0.75, close to 0.77 ampere meter square. Now there are two options. You see, option B as well as option C is 0.77, but one is in z axis, another one is in y axis. Now I would say that my magnetic dipole moment is a vector quantity and it is a cross product of ni and a, that is the area vector. So I would say it will be perpendicular to the xy plane, that means on the z axis. Option B. The susceptibility of a paramagnetic material or substance was found for different temperatures, and a graph of x against, so x versus 1 by t has been plotted. From the graph it was found that when x or susceptibility is equals to 0.5, 1 upon t is 5 into 10 raised to minus 3 per Kelvin. What is Curie's constant? Now we all know susceptibility is inversely proportional to temperature. Therefore, susceptibility is equals to C upon T. So we can say C is equals to susceptibility into T. So therefore C is equals to 0.5 into 1 upon 5 into 10 raised to minus 3. So this becomes 5 or 0.5 into 10 raised to 3 upon 5, which is 0.1 into 10 raised to 3, that is 100 Kelvin. C. The next question. A straight wire carrying current I is turned into a circular loop. Okay, so I have a wire which has been turned into a circular loop. So the length is L. Here L is equals to 2 pi r. If the magnitude of magnetic moment associated with it in MKS unit is m, so I would say magnetic moment is m. What is the length of wire? So here we require an expression. First of all, we'll see That magnetic dipole moment is current into area. Actually it's NIA, but here there's only singleton, so I would directly prefer N as 1, so I into A. I into pi r square, where r is the radius of the circular loop. From here r square is equals to m upon I pi. So therefore r is equals to under root of m upon I into pi. Now if I multiply both the sides by 2 pi, this becomes 2 pi r, and this becomes 4 pi square m upon I into pi. Pi and square will get cancelled, so therefore 2 pi r is nothing but length, so L is equals to 4 pi m upon I. Option C. To which logic gate does the truth table given below correspond? Now if you observe this table, this gives me 0 0 and the output is 0. 0 1, the output is 0, 1 0, output 0, 1 1, the output 1. So this reminds me of the table A dot B, and A dot B is nothing but AND gate. Option C. Two springs of force constants K and 2K dash are stretched by same force. Alright. So here the force constant is K, but here it is 2K dash. It's not the double of K, it's a different force constant 2K dash. So it's a bit of a tricky question. If W1 and W2 are energy stored in them, energy, that means it will be potential energy W1 and W2, then relation between them we have to find out. Okay, we all know F is equals to minus kx. Now F is equals to minus kx for F1 is my equation number 1, and F is equals to F2 is equals to minus 2k dash x. This will be equation number 2. So therefore, as since the force is equal, F1 is equals to F2, I would say minus kx is equals to minus 2k dash x. Minus minus will get cancelled, x and x get cancelled, so k is equals to 2k dash. Therefore k dash is equals to half of k. This relation is very important. Now let us find out the relation between your potential energy and k. W is equals to half kx square. From here we can say W is directly proportional to k. So for W1 upon W2, it will be K1 upon K2. For me, K dash is my K2 and K is my K1. So therefore, W1 upon W2 is equals to, you see, K dash is half of K. That means K is less than K dash. So K dash is half of K and W is directly proportional to K. That means W2 is equals to half of W1. Therefore W1 is equals to 2 into W2. Option B. Two particles P and Q of equal masses are suspended from two massless springs. Alright, so we have two particles P and Q of equal masses suspended from two massless strings. So first mass is P, the second one is Q. K1 and K2 are their spring constants if their maximum velocity during their oscillations are equal. So V max of first is equals to V max of second. Then the ratio of the amplitudes has been demanded. So A1 upon A2 is equals to question mark. Now when these particles are oscillating, their maximum velocities are found to be equal. So first of all, the formula for V max is A omega. Therefore, for Vm1 it is A1 omega 1, and for Vm2 it is A2 omega 2. Equation 1, equation 2. As we observe the options are given in terms of spring constant. So that means we have to put omega as root of k by m. Therefore, A1 root of k1 by m, since the masses are equal, I won't write m1 and m2, is equals to A2 under root of k2 by m. So therefore m and m will get cancelled. A1 upon A2 is equals to under root of k2 upon k1. Option D. A simple pendulum is suspended from the ceiling of a lift. When the lift is at rest, its periodic time is T. Okay, so when the lift is at rest, time period is T. What should be, with what acceleration should be the lift accelerated upwards so that the period of pendulum becomes T by 2. Okay, so I would say T1 is equals to T and T2 is equals to T by 2, and we require acceleration to be given to the lift so that T becomes T by 2. First of all, we'll write the formula for time period of simple pendulum. T is equals to 2 pi under root of L by G. From here, if keeping every physical quantity as constant, only G, so T is inversely proportional to root of G. Now, since it has to be accelerated upwards and it is inversely proportional to root of G for the second condition, so if this is T1, for the second condition T2 is equals to 2 pi under root of L upon G plus A. Therefore T2 becomes inversely proportional to root of G plus A. So on taking the ratio, I would get T1 by T2 is equals to under root of G plus A by G. On squaring both sides, I would get T upon T by 2 the whole square is equals to G plus A. As we see, it is T and T by 2, T and T will get cancelled, this will become 4 is equals to G plus A upon G. Therefore 4G minus G is equals to A, so therefore A is equals to 3G. So we require an acceleration of 3G in the upward direction so as to make the time period as T by 2. Now the next question is, select the wrong alternative for a particle executing SHM. The kinetic energy is given by. So different equations for kinetic energy has been given and we need to select the wrong option. First of all, we'll write the general formula of kinetic energy. Ek is equals to half k a square minus x square. If I put k as m omega square, this equation becomes like this. Now half m omega square a square minus a square sine square omega t plus alpha. Alright, how did we get this? Now putting x here as a sine omega t plus alpha. Therefore this equation now becomes half m omega square a square coming as common 1 minus sine square omega t plus alpha. 1 minus sine square theta is cos square theta. The half m omega square a square cos square omega t plus alpha. So we have this in equation 1. So equation 1 is correct. Also we have equation D as half k a square minus x square. So equation 4th is also correct. Let us solve it further. We have E total into sine square omega t plus alpha. But here if you observe, this is E total half m omega square a square and it is multiplied by cos square omega t plus alpha. So the option Bombay is straightforward wrong. So I would say option 2 is incorrect. Now the remaining option C will have to be correct because option B we have already determined as the wrong option and we need to select the wrong alternative. If Vm and Am denote the maximum velocity and maximum acceleration of a particle performing SHM, then amplitude of SHM is okay. So Vm is Vmax and Am is Amax. We all know Vmax is equals to A omega and Amax is equals to A omega square. If we square Vmax, so Vmax square is equals to A square omega square. This is my equation number 3, 1 and 2. So if I divide 3 by 2, I'll get Vm square upon Am is equals to A square omega square upon A omega square. Omega square got cancelled, A and square gets cancelled. A is equal to Vm square upon Am. Here option A resembles it. So we have next question. The period T of a simple pendulum is measured for different lengths. Then the graph of log T against log L is. Now this is a typical question and also very important regarding the CET examination. So we'll see. T is equals to 2 pi under root of L by G. So here I get T is equals to 2 pi root of G into root of L. If I focus 2 pi under root of 2 pi upon under root of G itself is a constant, I would replace it by K and I can write L raised to half in case root of L. Therefore, if I take log now on both these sides, log t is equals to log of k L raised to half. I can say log of a into b is log a plus log b. I would say a and this is b. So I have log of L raised to half plus log of k. Log of a raised to m is m log n log m. A raised to m is m log a. So I would say this is half log L plus log k, and this is log t. Now if I focus on this equation and compare it with the general equation of line, this becomes y m x plus c. Log k itself is a constant, log L becomes my parameter, log t becomes my parameter on y-axis. Therefore m is equals to, that is slope is half. Therefore it's a straight line with slope half, and that's option C. A small steel spear tied at the end of a string is whirled in a horizontal circle with uniform circular velocity omega 1. The string is suddenly pulled so that the radius of the circle is halved. Alright, so I would say R2 is equals to half of R1. If omega 2 is the new angular velocity, then therefore initially it was omega 1 and now it's omega 2. We need to establish a relation between omega 1 and omega 2. Initially the ball or steel sphere is tied at the end of the string and made to whirl. Therefore, and now when the radius or the string is pulled by half, I would say angular momentum is always conserved. So L1 is equals to L2, that is I1 omega 1 is equals to I2 omega 2. So therefore I have mr square omega 1 is equals to mr square omega 2. From here omega, or that's r1 and r2, omega becomes inversely proportional to r square. Now most of the students do this mistake because they use law of conservation of angular momentum over here. But now as we know, this r is not the radius of sphere, this r is the length of the string. So we cannot use this r because here it represents radius of sphere and we need the length of string as r. So this relation becomes incorrect. So you don't need to use law of conservation of angular momentum in this case, as it is followed by some books. Now the correct method is, we all know V is equals to R omega. Now this R represents the length of the string. Therefore omega is equals to V upon R. Therefore omega is inversely proportional to R. Now when I focus over here, R2 is half of R1, that means R2 is less than R1. So if this is omega 1 inversely proportional to R1, omega 2 inversely proportional to R2. So if R2 is less than R1, omega 2 is greater than omega 1. That means omega 1 will be less than omega 2. Option C. A particle moves along a radius of 10 centimeter. Alright, so we have radius as 10 centimeter If its linear speed changes from 4 meter per second, so v1 is 4 meter per second, v2 is 5 meter per second, in 1 second I would say it's dt time interval, angular acceleration has been demanded. So we need a relation of angular acceleration with linear velocity. We have a formula, a is equals to r alpha. So therefore alpha is equals to a upon r. I would say this is 1 upon r and bracket v2 minus v1 upon dt. Absolutely, because rate of change of linear velocity is called as acceleration. So this becomes 1 upon r, or basically it's 1 by 10 into 10 raised to minus 2. That's in meter. v2 is 5 minus 4 upon 1. So this is 1 entirely. So 10 into 10 raised to minus 1 is 10 raised to minus 2 is 10 raised to minus 1. It goes up, becomes 10 raised to 1, which is 10 radians per second square. Option C. Next question. A body is tied at the end of a string and whirled around in a horizontal circle. Okay, so it's kind of a conical pendulum, I would say. At any instant, its kinetic energy is found to be numerically equal to the centripetal force. So they have given us kinetic energy equal to centripetal force, that the radius has been demanded. So r is equals to question mark. Now we all know kinetic energy is half mv square and centripetal force is mv square upon r. Straight away we get r is equals to 2 meters. Option C. The string of a pendulum of length L is displaced through 90 degree. Okay, so initial position is this and it has been displaced through 90 degree. So this is my new position. Angle here is 90 degree, that is pi by 2. Then the minimum strength of the string in order to withstand the tension. So here we require the tension when it passes through the mean position. Okay. The minimum strength of the string in order to withstand the tension as the pendulum passes through the mean position. Okay, so the pendulum has been displaced to 90 degree and then it has been released, and when it reaches this point we require tension. We all know this equation, that T2 minus T1 is equals to 6 mg. For our assumption, we assume that T1 has to be 0 because at the highest point there is no slack condition. So if we put T1 as 0 over here, T2 is equals to 6 mg. Option D. Now this is one good question. A train has to negotiate a curve of radius 400 meter. So I'll draw a curve of radius 400 meters. Now the speed of the train is 72 kilometers per hour. So V is 72 into 5 upon 18. So I get 20 meter per second. If the distance between the two rails is 1 meter, so this distance is 1 meter. Sometimes the question could be asked like that, that a train has to negotiate a curve of radius 400 meter and the rail is of meter gauge. So meter gauge gauge is the distance between these two rails, and meter gauge means 1 meter. So it's not necessary that they will mention 1 meter as a distance over there. Then the outer rail will be raised over the inner rail. So this is a problem based on banking of roads, and if this is the horizontal position and this is the distance between the rail, I need h. This is my angle of banking and this is 1 meter. So if apply sine theta over here, this becomes h upon d. Therefore h is equals to d sine theta. H is equals to sine theta. Now in banking of roads, we have one formula which deals with the term theta and velocity, that is v is equals to under root of rg tan theta. We all have heard this formula. Therefore v square is equals to rg tan theta. Therefore tan theta is equals to v square by rg. Therefore theta will be tan inverse of v square by rg. Now what do you have v square as? So v is 20, so this becomes 400. R is already 400 and g is 10. So this becomes tan inverse of 0.1. So this is tan inverse of